Okay, good afternoon. So let us continue the lesson. Last time, if you remember, we started the new topic of combinatorics, and then we started learning very trivial principles that probably also are familiar with from the primary school. But we want to look into it a little bit deeper, and that was the product rule. Yes. So we started with the simplest version of the product rule. And that was that if I have a task that can be accomplished after two stages, and if the stage one can be done in n different ways, and after the first stage is done in any one of those ways, independent of how it is done, the second stage can be done, for example, in m different ways. Then for accomplishing the task, I have n times m different ways. Yes? And then we also talked about how we can generalize it to tasks with more than two stages. So let us, for example, review it for a task that can be accomplished in three stages. For example, if I ask you, give me a three-digit number, this task can be accomplished when I ask you to write a three-digit number. You even don't probably think about it, so you just write something like this. But if you want to analyze what your brain has done, you would say that you have decided something for the first digit, decided something for the second one, and decided for the third one. And I made a little bit stupid mistake that time. This is called the units digit. This is called the tens digit, not the 10th digit. So let me, I gave you a comment in the YouTube. So if I have this number, this number is the units digit or the ones digit. And this number is tens digit. And this number is hundreds digit. But if I go after decimal, that is reasonable, yes? It is 10th digit. And then the other one is 100. So I just was confused myself, okay? So that is one thing. And the other one, so you see here, when I write 159, it means that I decide to write 1 here, 5 here, 9 here. So it means that I am accomplishing a task which can be broken down into three stages. But it comes so naturally and fast that I even don't bother to think about it. I really recommend you, when you are dealing with combinatorics, try to analyze what is going inside your brain. That is probably a little bit vague, but it becomes clear in a moment. Okay, so if I want to write the product principle or the product rule for a task that can be accomplished in three stages, what can I write? I can say that assume the first stage, stage number 1, can be done in n different ways. And after stage 1 is done in any one of these ways, stage number 2 can be done in m different ways, independent of how the previous stage is done. And now assume that the stage number 3 can be done in p independent, p distinct ways, independent of how the previous stages are done. If this is the case, then to accomplish the task, meaning to do stages one after the other, then I have n times m times p alternatives. And then you can generalize it to a task with more than three stages. Okay, today it seems trivial. This is the first encounter of any novice student, but combinatorics is probably one of the hardest parts in mathematics. So you really need to be very smart to develop these kinds of tricks and techniques. So let us try to solve some examples. So mainly I will just try to give you different examples and try to discuss about. Okay, and one crucial point, do you remember I told you that sometimes the best way is not the natural order. Do you remember I gave you an example? For example, if I ask you to write a two-digit number, you can write 1, 2. So natural order is to take this one as stage 1, this one as stage 2. But sometimes you realize that if you want to follow the natural order, the product rule is not directly applicable. And I gave you an example that if you interchange the role of stages 1 and 2, then suddenly the product rule becomes applicable. And I told you that again, that for harder problems, even if you change, might be the product rule is still not applicable. So these are the salient points of what we have discussed so far. Okay, so let us see what examples we can have right now. Okay. So if I give you this word, almost, but these are, by the way, this is good to know. I give you a word, almost, and I say you that in how many ways you can choose a consonant and you can choose a vowel. I ask you to give me two letters from the letters here, but one vowel, one consonant. In how many ways you can give me that pair? In how many ways I can choose one vowel and one consonant from the letters in this word? By the way, this is a convention. When I write almost, if M is not repeated, it means that you're only allowed to choose it once. For example, if I give you book, if I talk something about the letters of the word book, it means that you have one B, one K, and two O's, not more than that. That's also convention. So here I ask you, okay, in how many ways I can choose a vowel and a consonant from the letters of this word? It's very, very simple. I'm just reviewing. Yes. How did you come to the answer? Can you tell me what is the task here? The task is exactly the problem. The task is choosing a pair of a vowel and a consonant. That is my task. So this task can be accomplished in two stages. Stage one, what do you want to call it? Choosing a vowel. Yes? So how many vowels are there? A and O. Yes? So in how many ways stage one can be done if you consider stage one choosing a vowel? So in how many ways I can do it? Two ways. Now stage two. How many consonants I have? L, M, S, and T. Yes? Am I right? Yeah. In how many ways I can do that? How many choices I have for stage two? How many? Four. But when you want to write 4, you have to be a little bit careful to convince yourself this number that I write here is always 4, independent of how I have done the first stage. And do you agree that this is independent? It doesn't matter if I have chosen A in the first stage, how many choices I have? I have 4 choices. And if I have chosen O in the first stage, I still have 4 choices. So the second one, you have to be a little bit careful. And then everything is done, so the total, the answer is 2 times 4, so which is 8. That's very simple. In this problem, do you think if I change the order, this will affect the result? No. The first one becomes 4 times, the second one becomes 9, and then we get this one. That was very simple. Now I have one question. I have a checkerboard, yes, not checkboard, checkerboard, I think is the correct one. Please correct me if you think I'm making mistakes. So let me just have a checkerboard here. I don't know, let me just 1, 2, 3, 4, 1, 2, 3, 4, 5 divided to 5. Let me see how many pieces I can put here. Yeah, 1, 2, 3, 4, 5, 6. Yeah, hopefully, yeah. So let me just draw this checkerboard here. It's not the standard one. The standard one is 8 by 8. But I just draw a checkerboard here. And hopefully, so assume that all these squares, actually they are all squares and they are of the same size. It is hard to draw them here. Now my question for you is this. How many 3 by 3 squares you can count here? Yes? So you see, let me write 1, 2, 3, 4, 5. So this is 5 units. Yes? How many are there? 1, 2, 3, 4, 5, 6, 7, 8. Now my question is that if I ask you how many 1 by 1, just 1 by 1 squares, Can you count here? It is very simple. How much is that? 40. But now I'm asking you how many, for example, 2 by 2 squares, or how many 3 by 3 squares? By the way, how many 6 by 6 squares you can count here? Nothing, yes? Because the width is 5. But if I ask you how many, let us fix something. How many 3 by 3 squares you can count here? For example, one of them is this guy. Yes, my picture is very, very poor, but hopefully you understand what I mean. This is one of those 3 by 3 squares. I can have another one, yes? For example, I can have this one. This is also another one. Okay? Now the question is that how many of these 3 by 3 squares you can count? But I want you to have a strategy for your counting. It is extremely important. And then I want you to really fully convince me that your strategy is really working. The loophole in combinatorics is double counting. Yes? Sometimes you think that you are counting in some way, but you are considering one or two cases more than once. This is very, very common mistake. So this is why, if you want to make sure that you are not making any mistakes, you have to define for me the task and then how many stages you want to divide your task into, and then start counting them and tell me that why each stage is independent of how the previous stage is done. I really recommend you to always think in this way so that after a while it becomes simple for you. The question is very clear, yes? And that's like a very childish game. You're just counting the number of squares there. Okay. So far, Dima is a volunteer, no one else. Let me just give you time to think about this. Yes, Dima?
So, when you increase the square,
yes,
for example, to be 2 by 2,
mm-hmm.
then the stages can be put in the squares in
mm-hmm.
horizontal,
Mm-hmm.
and there's only 7 possible.
Yes. Yes.
And then when you move down,
yes,
that can be the stage 2 when you move down.
Yeah, exactly. The strategy is working. So what actually he's saying is that let us concentrate on one of these typical squares. So what Dima is mentioning is that if you broaden your perspective and see that if I have this square, what can I do? I can take this as a horizontal axis and this one as the vertical axis, and then I project this here. Then I will get this point and that point. Yes? And then if I project this on the vertical axis for this red square, I get this one and that one. Is that understandable? So, here first I gave you the square, you gave me these 4 green points. But think it the other way around. If I have given you the 4 green points, could you construct a red rectangle for me? Is that understandable? Yes or no? Because assume that, for example, if you don't know this red square, I give you these 2 points here, a pair of points here, a pair of points here. The distance between this pair is 3 units. The distance between these 2 pairs is also 3 units. Then I draw 2 vertical lines here, draw 2 horizontal lines from here. They will start intersecting. Then my square becomes clear. Is that understandable? So, there is a one-to-one correspondence between these squares, okay, and the number of choices that I have for these 2 points and those 2 points. Is that understandable? So you have to make a model for yourself. So I would say that because now I understand what is going on, I can say that this task can be viewed in a different way. I would say that my task is to find a pair of points with distance 3 on the horizontal axis and a pair of points with distance 3 on the vertical axis. And this task can be accomplished in 2 stages, stage 1 and stage 2. The stage 1, for example, let us focus on the horizontal axis for stage 1. How many choices I have if I want to find a pair of points whose distance from each other is 3 units? Yes, I can keep my hand like that. This is one choice. Do you agree? And then this is the second choice. Yes? And then this is the third, this is the fourth, this is the fifth, and then finally this is the sixth. Am I right or not? No, it should be 7. Yes? Or no? That's 6. Yes, you are right. So the number of choices that I have for this stage is 6. Yes? Let me check it again. So this is 1, 2, yes, 3, and then 4, 5, and then 6. So I have 6 choices for this pair. How many choices I have? So assume that stage 1 is done. What is the meaning? Assume that you have chosen a pair. For example, this one. Now let us move to the second stage. I want to choose a pair whose distance from each other is 3 units. Yes? How many choices I have? This is one choice. This point and that point. And this is second. And this is third. So, stage 2 has 3 options. But before making sure that I am allowed to write 3, I have to check the independence. Is this number always 3 or it depends to the choice of the previous stage? So if I have chosen this one, I have 3 options. Do you think if I have chosen this pair, this will affect this one? No, this is still 3 choices. So this number that you put here is independent of how I have done here. So if I multiply, so the product rule is applicable, and then it becomes 6 times 3 is how much? Is 18. By the way, let me emphasize that the task is not done until the last stage is done. Yes? So this is crucial because you want to have them simultaneously. That your task, which is making a square, is only done when a stage 2 and a stage 1 are both done. If you just do a stage 1, your square is not done yet. Okay, so that is also one thing that you... So you see that it was very simple to count it in this way. Yes? And I hope that you agree that this is working. Yes? So there are only 18. Is that right or not? Yes? Okay. This is one question. So another question I want to ask you. Do you remember in set theory, I asked you this simple question and I told you that you will prove it later. So for example, if I give you a set consisting of 3 distinct letters, 3 distinct objects, how many subsets are there? Do you remember? I gave you the formula, but we didn't discuss the proof, but we can now prove it. Okay, first of all, do you remember the formula? So how many subsets? What is the smallest subset? Totally forgotten or not? Do you know? Yeah? The empty set. So the first one in the list is the empty set. Yes? What is the second one, for example? I can write A, I can write B, I can write C, and then A and B,
and then A and C,
and A and C,
and then B and C.
and B and C. Do I repeat them? Can I write B and A again?
That's not necessary.
No, you shouldn't write it because they are the same.
Oh, yeah.
So these are the only subsets of that. And how many of them are there? 1, 2, 3, 4, 5, 6. And then? Yes,
Yeah.
A, B, C. So thank you. 8 of them. So there are 8 of them. Do you remember what was the general formula? If I have 3, it was 8.
Yeah.
I don't know, if I have 4, how many of them are there? Yes?
2 raised to the amount of...
Yes, to the number of elements. 2 to the power of n. So the cardinality of the power set, okay, forget about these things. So the number of subsets is 2 to the power of 3. But can you tell me why? If I ask you to write them down, this is the only way. But if I ask you how many of them are there, of course this is also one way to answer. List all of them and count them. But assume that this is going to be 1,000 elements there. Then it would be not possible, or not practical actually. So how do you have any strategy to count them? You see, the question is very simple. and this needs the product rule. But how? Think about what your brain is doing. It's really, I don't know, let me just explain this. So for example, I give you a set. Let me, if you don't mind, let me, for example, ask Dila. Give me a subset of this set. Just tell, I put curly brackets here, curly brackets here. Give me a subset of this one, whatever you like. A. Okay, but now can you analyze what happened in your brain?
I just read those who were in the set.
Okay, but you see, okay, now does this help you to find a strategy? Because I asked Dylan what it give me a subset. Dylan gave me put A there and then he stopped. But if you analyze what is happening in your brain, you are making decisions 3 times. Yes? I don't know. You look at A because you want to get an A always. So you put A there. And then say that I don't want to get B and C, so let us ignore them. What I'm meaning, it means that you are making 3 decisions. Yes? You made a decision for A. For some reason, you wanted it to be in your subset. And you chose not to choose C, B, and C. So you made 3 decisions. Is that understandable? And in each case, how many possibilities you have for your choice in your decisions? Yes? 2. Yes, because you say that I decide about A. I have 2 choices. Either I like it and put it there, or I dislike it and throw it away. And then I go to the B. Either I like it and put it there, or I don't like it and throw it away. And the same thing for C. So it means that writing a subset is actually a task, in this case, with 3 stages. Stage 1, making a decision about A. Any sentence that you want to write it. Stage 2 is making a decision for B. Stage 3 is making a decision for C. Yes? How many ways I can do the stage 1? I have 2. Now assume that stage 1, I have 2, and I do it. What do I mean I do it? It means that either I decide A to be there or not. I make a decision. And when I go to stage number 2, I want to decide about the situation for B. How many possibilities I have? 2. Is this 2 independent of my choice? Yes, it doesn't matter if I like it or dislike it, but still for B, how many choices I have? 2. And then for the stage 3, how many choices I have? 2. So is the product rule applicable? Is the product rule applicable? Yes. So this means that this becomes 2 times 2 times 2, which of course is 2 to the power of 2. And of course you realize that this is not very sensitive to the number of terms, yes? If I give you 4 elements, if I give you 5 elements, you can follow the same strategy with 4 stages, with 5 stages. So this is the reason that the number of subsets is 2 to the n. Is that clear? Yes or no? Okay. Now let me ask you one question. How many binary codes are there with 3 digits? So the difference between, so this can be a binary code. Okay? But this is not a 2-digit, it is not a 3-digit number. When you say code, you can start with 0. Okay? When you say a number, you cannot start with 0. That is the difference between a code in this case. Now, can you tell me how many 3-digit binary codes are there? How many 3-digit binary codes are there? Yes?
8.
Okay. How do you say that?
It can either be 0 or 1.
Exactly. So again, a 3 binary code is a 3-stage task. When I wrote 0, 1, 1, my brain decided about this code, and that code. But I have only 2 possibilities, 0 and 1. So again, that's the same story. Is that understandable? Yes? Okay. So this is one of the questions. Now let me make the question a little bit more interesting. So now I give you a 4-element set. So I want you to memorize that. That is good to know. If I ask you the total number of subsets, You understand why? The answer is 2 to the 4. But now I ask you one question. How many subsets are there so that A is not in any of them? So how many subsets are there that they don't include A? They don't contain A. How many subsets of this set you can write down so that in none of them A is present? Yes, Kevin?
I think 8.
How?
Because for every choice of A, you can only choose to not bring it. So
Mhm.
that's 1 in the product rule.
Yes.
And then for every other, you have a 2.
2. Exactly. You see, again, how many stages are there? So you can consider in 2 different ways. There are 2 alternatives. When you say that A is not present, in the beginning I just throw A away from my game, yes? And then I am left with these 3. But how many options I have for B? 2 options. Either I choose it or this choose. I don't choose it. And then this one and this one, it becomes A. Or I can say start from the beginning. I say that I can see it as a 4-stage task. But stage 1, how many options are there for stage 1? I am not allowed to choose it, yes? So it means that I have only 1 option. So this becomes 1, but others become 2. So if you multiply them, it becomes 8. Yes? So now let me ask you this question. If I give you this subset, A, B, C, D, E, F, G, in how many subsets A and B are present, but G is not present? In how many subsets of this 1, 2, 3, 4, 5, 6, 7 element set, A and B are present, but G is not present? How many? Or at least tell me what to do, yes?
16.
I don't know, I have to calculate, but can you tell me your strategy?
A has to be included, so A, there's only one option.
One option left, yes?
And the same for B, so it's also 1. Then 2 for C, 2 for D, 2 for E, 2 for F, and 1 for G.
Exactly. Yes, so now you can answer this question. But still, the very nice question that you cannot answer right now is that how many 3-element subsets are there? Yes? So I ask you, of course, you can start writing all of them. So for example, A, B, and C is one of the subsets of this with cardinality 3. Another one is A, B, and for example, F. I want to see how many 3-element subsets are there. But this is a little bit more advanced. We will study that, but not right now. You need to wait a little bit. Okay, any questions here? Okay, now let me ask you one question. I want to wait for you to solve it for me. So example, I give you a set 1, 2, 3, up to 10. Consider this set and I ask you in how many subsets, so let me give it a name. The question is that, in how many subsets of A, 4 is the smallest number? Okay, please do not tell your answer until the time is finished. So I want you to think about it yourself. It's very, very simple. You need to read it and interpret it in your own way and find your number. And then we can discuss about that. Of course, I should write is for the smallest number, yes.
Okay, that.
Yeah.
That's okay.
Okay, so let me add one more part to it, and then you can think about both of them. In how many? Is 3 the smallest and 8 the largest element? Okay, so do you have your answer now? Yes? So I don't know, I haven't calculated myself. So the question is clear, yes? I give you a 10 element set, and then you're supposed to find a subset. Yes? I haven't mentioned how many elements should be there or not.
No.
Okay. So in how many subsets of A is 4 the smallest number? For example, is this acceptable or not?
No.
This is not acceptable, yes? Because the smallest element is not 4. Okay? So you understand the question, but one way is to list all of them and try to count them, which is time consuming. But one is that we should be a little bit smarter to find a strategy to use at this moment. The only rule that you know is the product rule. So in principle, you should be able to use the product rule in an efficient way to calculate this, to count it. Yes, Dina?
We can create a new list that excludes 1, 2, 3.
Yes.
And then we have 4, 5, 6, 7, 8, 9, 10.
Yes.
And then we can say that 4 has to be included in every, so we
Yes.
get that as 1.
Exactly. So you are again making decisions for each one of those elements. Yes. When it comes to 1, how many options you have? So you can assume it as a 10-stage task. Yes. So you decide about 1, but because of the condition of the problem, you decide to exclude it. Yes. So exclude it. Yes, not exclude. You decide to exclude it. So that would be how many. So how many options are left for you? If there is no constraint, I have 2 options for 1, 2 options for 2. But now I have 1 constraint. I want to have 4 as the smallest element. So I am not allowed to put 1. Otherwise, 1 will be the smallest element. Yes. So I decide. So you see, a stage number 1, stage number 2, let me write them. Stage number 3, stage number 4, stage number 5, stage number 6, 7, 8. You don't need to write these details, but I just want you to understand it better. So stage number 1, making decision about 1, stage number 2, making decision about 2, etc., etc. So how many alternatives I have for stage number 1? Only 1, because I know that I have to exclude 1. What about 2? 1. What about 3? 1. What about 4? 1. But I have to include. Yes?
Yeah.
These ones means exclude, but then this one means include. Yes?
Good.
But again, I don't have 2 options. I have 1 option available. So this is exclude. Yes? And then here, how many options I have? Yes, 2. For this one, 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 2. Yes? And I hope that you agree, these 2's that I have written here, all of them are independent of my choices in the previous steps. So then the answer
power.
Why this is a product? Be careful. Now the only rule that you have is the product rule, so you know somehow that you have to multiply. But later you have to decide. Either you have to add or you have to multiply. Should I multiply? Yes, because my task is to make the decision for all of them. This task is only accomplished if I start from stage 1 and do it up to stage 10. I have to do all of them. Yes, otherwise the task is not accomplished yet. So then it means that the total number that I am looking for is 1, 2, 3, 4, 5, 6. Of course, if I want to be very strict, I have to multiply these numbers as well. 1, 1, 1, and then 2, 2, 2, 2, 1, 2, 3, 4, 5, 6. So which of course becomes 64. Yes? But how many subsets are there? 2 to the power of 10,
Yes.
which is 1024. So out of 1024 of them, only 64 of them have that property. Yes? And now I really want you, the people who are interested in coding, I want you to be able to write a code so that it writes every one of them with that property and count them. So that will be a very good exercise in programming. So if you are interested in that, try to write a very simple code that generates all the subsets that you like, not using the combinatorics. Just generate all of them, and then you know how to count them by programming. And count them and see that it is exactly this number or not. It's a very, very nice exercise if you like programming. Yes?
Can't you see it as 7 stages?
Yes, that is up to you. But at least you need to have your task defined in your head. Yes? Might be, I don't understand your strategy, but when you explain, I understand that this is work. Yes? So you might say that, okay, forget about these things. Yes? Or I can say that this is a 6th stage, yes? Because I can forget about these things. Yeah, that's up to you how to decide. Yes? Okay, now can you solve the second one? The second one strategy becomes clear, so if you don't mind, let us not waste so many minutes on it. So stage number 1. Here, the smallest element is supposed to be 3, but there is a maximum element demanded by the problem that is supposed to be 8. Okay, so now tell me, if I want to solve that one, how many options I have for stage 1?
Wow.
Yes, because the smallest one is supposed to be 3, so it means that I have to exclude these.
And 2, yeah.
Yes? But what about this one?
Also, I think.
Also 1, but this one is including.
Yes.
Yes? And then when I go here,
2
2.
until 7.
Yes, 2, 2, and 2. But 8 should be
1.
included, 1. What about this 9 and this 10?
Excluded.
Excluded. So 1 option. So 1, 2, 3, and 4. So there are only 16 of them.
Yes.
Again, if you like coding, write a code so that generate all of them. And then count them by just really counting them. Okay, so the answer to this one is 2 to 16. The second one is 16. The previous one was 64. Okay. Now let me ask you another question. That's also an interesting question. If I give you 2,400, okay, and I ask you, tell me how many positive integers are there? How many natural numbers? It is better. How many natural numbers are there so that this number is divisible by them?
How many
So for example, 2 is one of them, because 2,400 is divisible by 2. 3 is one of them. I don't know, 400 is one of them. Yes? In total, how many of them are there?
What was the question?
The question is that how many natural numbers are there so that 2,400 is divisible by them?
Okay, divisible by 2.
So the smallest number is with that property is?
2.
No, even smaller.
1.
1. The largest one is?
2,400.
Yes. And there are some numbers in between. Of course, that is simple. You can just write all of them and count them, but that's boring. Now my question is that I want to pause the recording again, and I want you to think about this. And if you can, after doing this, find a general formula for that, or a general strategy for answering not only for this number, for any number that I give you. Yes? So let us stop a little bit. this question is good because it is not directly related in your brain with the product rule. Yes? So you see, in these kinds of problems, coming up with a strategies is the important part.
Strategy.
So your strategy should be in a way that you can adopt the product rule to solve it somehow at this stage. Of course, it becomes more complicated if we have different rules. Okay, so any strategies? Yes? No ideas? You see, the combinatorics questions are easy to design but hard to solve. And that's the nature of this, especially in discrete mathematics. Okay, so I don't know, do you have any idea? Yes?
I don't know if it's...
Yeah, just
But
please.
if you divide it up into grundpotensform, like in the prime numbers.
That's
so-
the best. Okay, so let us do that.
But this is not a prime number.
Okay, so
Oh, they didn't say it.
can you, first of all, I told you that when we were dealing with number theory, I told you that of course you can't, I don't know, this old method to factorize, you divide by 2, it becomes this one, and then you divide by 2, it becomes, all the numbers that you put on this right column should be a prime number. And then this process, if you continue, will end up with 1. But that's a little bit boring right now because this number is so big, but it ends with 2 zeros. So this means that if I want to do it, I can do it in this way. Yes? But this is how much? Is 2 to the power of 3 times 3. Agree? 8 times 3. And then this is 2 times 5. This is 2 times 5. So I have 3 2's here, 1 here, 1 here. So it is 2 to the power of 5. Yes? And then I have 3. And then I have 5 to the power of 2. Agree? So if you don't believe, you can multiply. This is how much? 32. And then if you multiply it by that, it becomes 96. 96 by 5 is how much? Yes, that's correct. Yeah, that becomes that number. Yes, I haven't done any mistakes. Is that understandable? Okay, but now do you have a strategy after that?
I just thought that all possible combinations of those 8 numbers.
Exactly. So it means that if I give you, for example, 21, is this number divisible by 21? Okay, how do we see that? Because if I factorize 21, what do I see in its factorization? 7, which is not there. So when I say that this is not divisible by that, because if I divide this by that, it is not an integer. Why is not? Because I write this, then I write 3 times 7 here. Of course, this 3 and that 3 are cancelled, but there is nothing to cancel this 7. So it means that it is not possible to get an integer out of it. And it means that this number is not divisible by 21. So in principle, it means that if I want to find the numbers for which this is divisible by that, it means that in those numbers, when I factorize, I should have only these factors with powers of 2 at most 5, with power of 3 at most 1, with power of 5 at most 2. Is that right or not? Okay, now can you tell me, in this case, what is my task by this strategy, and how many stages can be defined for this task? Now I think everything is clear. So my goal is to write a number. So you see, I would say that task, writing, I don't know what you want to write. Let me write it in this way. Writing down a natural number n, so that 2400 is divisible by n. I don't know, you can write whatever you like, meaning the same thing. This is my task. Okay, so and can you split this task into how many stages? 3, yes? Because what prime numbers are important for in this case? Because I factorize that and only 2, 3, and 5 appears, so it means that I need to care this number n. You know that this number n can be factorized, yes, to prime numbers. So I can factorize it to 2 to the power of alpha 1. I don't know, 3 to the power of alpha 2, which I don't know what are these things, but I know that I can factorize it like this, yes? I can factorize my number like this. And if I ask you what are these alphas, you would say that alphas are non-negative integers. The lowest value for an alpha is 0, and the highest value of alpha, there is no upper bound for highest value, but here I know that alpha 1, there are some few choices for alpha 1. What is my choice for alpha 4, for example? 0, because if there is at least 1 7 here, this is not possible that this is divisible by that. So it means that I really don't need to bother about after this one. Everything should be 0, 0, 0, 0 for powers. So I need to concentrate here. But how many choices? So you see that this is a 3-stage task. Choosing a proper number for alpha 1, choosing a proper number for alpha 2, and choosing a proper number for alpha 3. So I was able probably to, by this strategy, to use the product rule. Okay, stage 1 is choosing alpha 1 properly. How many choices are there for a stage 1? 6, not 5, yes? Because one choice is that has totally ignored that. So you can choose alpha 1, 0, 1, 2, 3, 4, or at most 5, not more. So how many of them are there? From 0 to 5, there are 6 numbers. So this becomes 6 alternatives for alpha 1. But how many alternatives do I have for alpha 2? 2. Because either I should ignore 3 or at most 1 power of 3. So, but be careful. Is this 2 independent of my choice for the previous step?
Yes.
Yes. Because it doesn't matter which number I have chosen for alpha 1. Still how many choices I have for the power of this 2. Yes? And now assume that this is done, I go to the third stage. How many options are available for this? 3. Okay? Okay, but this task, all of these stages have to be performed so that I am relieved to find n. So it means that I can multiply. 6, 2, 3. So the answer is how much? 36. So you see, that is I would say that's a highly non-trivial problem, yes? But we were able to determine that there is exactly 36 of them. Is that clear? But if I ask you how many divisors are there, what do you say? Divisor exactly is the same thing, but when you say divisor, it might be positive or negative. So you multiply this number by 2. Because for any positive number, you also have the corresponding negative. Okay, but I hope that you agree that this is indeed really powerful. Yes? Because we started with a very trivial thing, but we are counting non-trivial things. Okay? Now, can you cook up a recipe for me? Can you cook up a recipe? For example, if I change my mind, and I give you this number, 48. By the way, how many positive divisors are there for 48? So now I think you know the strategy. What is the first thing to do? Is to factorize this. But this is 16 times 3. 16 is 2 to the power of 4 times 3. So how many of them are there? 5. 1 more than that, multiplied by 2. So there are 10 of them. Yes, so there are 10 of them. So you can count them, by the way. What is the first one? 1. The second one, 2. 3, 4, 6, 8. The next one, 12, 16, 24, and I think 48, yes? These are the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have exactly 10 of them. Okay, let me change the question a little bit. Okay, I give you exactly the same number, 2400, and I ask you, how many positive divisors are there so that that divisor is divisible by 6? So how many divisors are there so that the divisor itself is divisible by 6? So for example, one of the divisors here was 1. But I need to ignore this in this new part. Because even though 1 is a divisor of 2400, but 1 is not divisible by 6. So I cross it over. So 2 was one of them again, but not in this case. So I have to drop it. Yes? Now my question is that, how many divisors are there so that the divisor itself is also divisible by 6? So how should I answer this question? Or at least give me the strategy. The strategy should be very, very clear. Yes, Kevin?
It's not a strategy, it's a question.
Yes, yes.
So to me, it feels like the stages aren't independent of each other when we ask this question.
This question?
No, this one, that the divisor should be divisible by 6.
No, but this question is your question is a little fundamentally wrong. Because you don't know my strategy. If I present my strategy to you, then you can say that no, your strategy is not according to the product rule, so you are not allowed to use the product rule. But you are actually jumping ahead. Yes, I haven't introduced you any strategies, but you are criticizing. No, any future strategy that you want to present will not work. Yes, that is what you are saying. Do you understand what I mean?
Yeah.
I haven't presented any strategy.
Okay.
Yes. Exactly. So that means that I have to modify these numbers a little bit. Yes. So here we still have that number 2 to the power of 5, 3, and 5 to the power of 2. Okay, but now I want to choose something like this as before. Still, I want to choose these numbers. If I do not have any constraints, the lowest value for alpha 1 is 0, the highest value of alpha 1 is 5. Yes? But if I choose alpha 1 to be 0, there is no hope the remaining thing is divisible by 6. Because to be divisible by 6, your number should at least have one factor of 2. So this means that now what is the constraint in this new problem? Alpha 1, how many options are there? It is 1, 2, 3, 4, and 5. Yes? I can choose only these numbers for alpha 1. What are the choices for alpha 2? Only 1. Because it should be divisible by 6, it should be divisible by 3 as well. And then what is alpha 3? What are the choices for alpha 3? I don't have any constraints here. 0, 1, and 2. So how many options are here? 1, 2, 3, 4, 5. How many options are here? Only 1. How many options are here? 3. If you multiply them, it becomes 15. Yes or no? Is that clear? Okay. Now let me ask you another question. That is probably a better question. The question is that, I want to wait for you because probably it's a very nice problem. How many 4-digit numbers are there so that the sum of its digits is odd. This is the question I want you to think about. I am not asking you how many odd 4-digit numbers are there. In that case, might be it is not that hard. You count all of them and probably divide by 2. My question is that how many 4-digit numbers are there so that the sum of its digits is an odd number? The sum of its digits. For example, is 1, 2, 3, 4, 1234 is acceptable. Is it a 4-digit number?
It's not.
But if I add the digits, 1 plus 2 plus 3 plus 4, what is the answer? What is the answer? Is 10. But 10 is even. So I have to exclude this. Okay? Again, for the people who like programming, write a program to write all of them. Okay? And now, let us go back. I want you to count this. How many 4-digit numbers are there? So that the sum of the digits is an odd number. Yes? Let me ask you one question. Let me test your intuition. How many 4-digit numbers are there? How much? 5,000? No? 4-digit numbers, yes. 9,000. Yes? Is it 9,000? Because the lowest one is 1,000, the highest one is 9,999. Yes? And if you subtract them, it becomes 8,999. But I told you the trick. You need to add one more. So it's 9,000. Now, do you think the answer to this would be 4,500? Yes or no?
It doesn't feel like
So how do you? I don't have a feeling for it right now. I don't know. Can you describe your feeling? Because if I ask you how many odd numbers and how many even numbers are there, might be you say 50-50. Yes? That is reasonable. But do you think the same answer will be for this one as well? Let us think. Yes. I want to wait for you. This probably would be an interesting problem.
Hur många jämna har
det slutar på en 3. Ja. Men den har ju inte om vi säger alla de
två jämna har
då kommer alltså säga att det är
Okay, the people at home, you understand the problem, yes? So I want to pause so you will not be able to see it. The question is that how many 4-digit numbers are there so that the sum of its digits is odd? I will pause the video now. Okay, any kind of a strategy? Do you have it?
I think so.
So what is the number?
I got 4,000.
How many of you agrees that this is still 4,500? Okay, tell me about your strategy.
Yeah,
May you speak louder, please? Thank you.
I divided it up into 8 stages.
8 stages.
Where the first stage consists of choosing the first number to be odd. And
Yeah, let me hear her. Yes.
I don't know if this is the right strategy.
No problem. But at least even if it is a wrong strategy, that is up to us to say which part of that is going wrong.
Yeah.
Because this is not easy, by the way, in combinatorics. It's really hard to see. Many times I have come up with a strategy, I was completely sure my strategy is not possible to be wrong, but then it turns out to be wrong. Yes, this is completely normal and natural in this topic. Okay, I want to listen.
So to create an odd sum of the digits, you need either 1 odd digit or 3 odd digits in the number.
Yes.
And there are 8 different ways of creating a 4-digit number
Yeah.
with those combinations. So it's the odd and the rest even,
Yes.
and on each position, and
Yes.
then 3 odd with
Yes.
1 even on each position.
Okay, so can you tell me, so if I ask you, if I want to understand your strategy, so if I ask you to define your stage 1, what do you say?
Stage 1 is choosing an odd first number and 3 even numbers.
Okay, choosing the first odd digit, you mean?
Yeah, the first,
By first, you mean, for example, if I have 1, 2, 3, 4, What do you mean?
Yeah, the first digit in the
The first digit.
yes. To be
So
odd,
choosing
and
the
rest
first digit to be odd.
even. Yes.
So let me write it in there. Choosing an odd digit.
In the thousands position.
Yes. For the first, I would say first is the left-hand side. For the leftmost digit. Okay, choosing an odd digit for that one. Okay.
So the rest are even.
Okay, so the rest are even. Okay. But then you are adding things, yes?
Yes.
Okay, so that is probably correct. So that's the point. So what she's doing, probably your strategy is working and it is correct, but you have decomposed it to separate parts and you have counted each part and then you are going to add them up. Yes, but you are just jumping a little bit ahead. Yes, because that would be, of course this is so trivial that you already know what to do, but that is the sum rule. Yes? And by the way, but there is one very nice strategy that you can count it with in one step just using the product rule. So what you have done now I understand is completely correct. Yes, and it will work. And I will talk about that later. That is called the sum rule. But now, if this is going to be an algorithm, if you want to write an algorithm to do that for you, then your algorithm would be longer.
Yeah.
Yes? But the optimization part when it comes to coding is is it possible to do the same thing with lower number of codes? And I think, when I was thinking, because that was the first thing come to my mind. And the reason that I thought a little bit, because when I was designing these questions, I put it under the title of the product rule. So it means that at that stage I remember something to do just with product rule. Yes, so that was the reason. Otherwise, this is the most natural way of thinking is this. Partition it to different parts, count each part and then add them up. Yes, but it is always very interesting that can you come up with a strategy that just needs one single product rule to answer the question? Yes? And I want to leave it open for you to think about it. And then, I don't know, I haven't thought, because you know that changing even a little bit the questions make the question very harder. I haven't thought about that. But can you think about the same question but with distinct digits? Think about that one as well. I haven't thought myself about it. I will go home and sit down and think about it. So first of all, try to come up with a strategy that you can solve this problem with one single product rule. Yes? And then after you are relieved and you got the answer, you will think about this, how many 4-digit numbers are there so that the sum of the digits is odd and they are of distinct digits. Let us think about this problem. I'm not sure that we can solve it by one single step, but let us think about it. Thank you very much. But I think your answer is correct. Thank you. So I end the meeting here for the people at home. Thank you very much.
Ja, sen så blev det...